Welcome to Radio Design 401. As we say at the bottom here, this is an advanced course and a white paper, whatever that is. It's an advanced course because we've already done a series on Radio Design 101. This is a blackboard from a course at a university which Radio Design 101 was patterned after. The goal of that class was to design an FM broadcast band receiver. And you can see the block diagram of it here. We're going to review that today. But Radio Design 401 is an advanced course. It relies on some knowledge of things like Radio Design 101, the material covered there. If you haven't seen those previous videos, here's what it looked like at the end of that. We put together a full FM broadcast band receiver, and we tested it out using equipment like the tiny spectrum analyzer and small oscilloscopes and so forth that people can generally buy for not too much money these days. And at the end of that video series, we had this working. We listened to it on these speakers and we picked up several channels, and it was pretty cool. But back to Radio Design 401. This is episode 1, part 1, and we're going to be talking today about low power radio receivers in crowded spectrum environments. And as we'll discuss, this is a challenging thing to do, and one that is not done that well in commercial products, quite frankly. So that's what the white paper notation here is about. And not everybody is familiar with that, so I went to Google, typed in what is a white paper, and the AI tells me this. It's a, hopefully, informative document, often used in business. In this case, this is a nonprofit channel just for education, so that's slightly different. But we're going to do this other stuff. It presents a detailed analysis of a specific topic, problem, and solution in our case, usually with the intent to educate the reader and persuade them to support a particular viewpoint or product, often by providing facts and evidence in a professional and authoritative tone. Well, I hope we can do that. So that's where we're headed in this video today. So in courses at the university, I always like to start off the first day with some review, because you can't expect people to remember everything they learned from the previous courses. And so here's our first day review. If we have a radio, it's built on circuit boards, and they have integrated circuit chips and lots of other components. I'm just abstracting that here. And there's an antenna that pulls in signals. And usually there's a signal you want, and there's a bunch of other signals that you don't want and that we call interferers. And there's also background noise that we'll get into today. So what does the spectrum environment look like? Well, that's shown up here. This is a sweep from 0 to 350 megahertz with a small antenna in my home office. And this is taken from this video on this channel if you want to look for it. But what we see here is all this stuff. This is a group of signals, which is the FM broadcast band, around 100 megahertz. Over to the left here, these are shortwave signals, and to the right, this is mostly noise from lights and equipment in my office. But there could be signals popping up here periodically. Now, as we discussed in Radio Design 101, receivers have what are called front-end filters, and probably a low noise amplifier. And the purpose of these is to block as many signals as we can and only let the ones that we care about through. And then they get what's called down converted to a lower frequency, and you strip off the signal you want and you pass that on to the demodulator. And so that's what all these circuits are doing here. In the lower left, these are the signals in my area. There are 24 stations in my area that I can hear according to this spectrum analyzer trace. We'll get into that a little bit more as we go. I put some markers on this one, and this one. And we're going to go into why that is later. But suffice it to say that there are very strong signals in my area, almost minus 20 dBm. That's a very strong signal. And then many of these are very weak. Like that one right there is super weak. This one's moderately weak. That one's super weak. This one is at what's called the noise floor, but only of this spectrum analyzer. This spectrum analyzer cannot detect signals that are lower than this. And we'll get into why that is in this course. So there you have it. This is our first day review. Now, at the end of the Radio Design 101 series, we had a working receiver that was awesome. However, getting something working is only the first step if you're trying to build a competitive product. You really need to make it work as well as possible. And so there were a couple, 2-3 epilogues of Radio Design 101 series that came after the main videos. And this is from epilogue 1. We compared the radio that we designed and built down here with a couple of commercial radios. This is a Yaesu wideband receiver, and this is an older Radio Shack wideband receiver. Now, don't let the age of these things sway you. Turns out this one performed better than this one, even though this one's newer. But we're going to build something that can perform better than any of these, and in fact, any of the newest radios at low power. So what does that mean, perform better than? Well, in this case, what I'm interested in is how many signals can I receive? And there's like this very weak one at minus 80 dBm. And this is the strong one at minus 22. So what's that? About almost 60 dB difference in signal power coming into the receiver. And only very good receivers will be able to get this weak signal in the presence of this strong one. So in epilogue 1, we measured the performance of these different radios, the one we built versus some commercial products. And here are the results. This is very busy, so I'm not going to go into it in gory detail, but if you look at the circled area here, this is a station at 98.5. That is this really weak one right here. And everything is blank here. That's because all of these radios could not receive that station. But let's look at the other stations and some of their signal levels. This is the really strong one, and of course our FM receiver, that's ours that we built, and then we modified it a little bit in the epilogues, made it work better. So even before we modified it, this station here at 96.3 minus 22 dBm, we could receive that perfect. And for these, I just said yes. Those were also perfect too. Now, the commercial radios could receive these signals at minus 55 dBm and minus 60 at these frequencies. Our radio, initially, it was pretty quiet. We could hear them, but it was pretty quiet. We added some extra IF gain, and then it became what I'll call good, but not quite as good as the commercial ones. But by looking at our design critically in epilogue 1 and epilogue 2, we were able to improve its performance quite a bit. So we got a lot of stations, but not quite as many as some of these other radios. And I'll let you look at that video, epilogue 1, if you want to go into some detail. And for example, why the older radio performed better than this newer VR120. And just to whet your appetite for what we're going to talk about, why that radio could perform better, the reason is these filters before the mixer were sharper. They were more narrow in bandwidth than in the other radios. We're going to come back to this slide later. But there was one other problem, and this problem exists in all modern radios except ones like in a car that have a lot of power consumption and are able to deal with it. Here's our spectrum again, and if we look at it, there's a very strong station at 96.3 that we said. There's also one at 93.3 megahertz. And then there's a moderately weak, I mean, it's not terrible, it's minus 75 dBm, station at 90.3. And we could not hear that on virtually any of the radios, except that older one. And the problem is due to something called intermodulation that we're going to go into in depth in this video series. But in a few words, strong signals like these at 96.3 and 93.3 can mix together. It's not exactly the mixer in your radio, but it's a similar phenomenon mathematically. And when they do, they can create another signal at a frequency, in this case 90.3. These are 3 megahertz apart, and then this one is 3 megahertz on down. And that signal that gets created in the mathematical mixing of these signals can block your ability to receive this signal. So let's take a listen to that. This is from timestamp 7 minutes 43 seconds into the final epilogue of the Radio Design 101 series. I'll just play a little snippet.
In a tight job market with plans to consider adoption on first reading at their April 19th meeting. The study recommended updates to job.
And I want to emphasize that the problem that this radio is having is not because it's older or anything like that. It's because of a fundamental issue that we're going to be discussing in this video. And we're going to show how this problem can be solved. This is a simulation of the frequency response for a new combined front-end filter low noise amplifier that we call a Q-enhanced LNA. Okay, so now let's listen to 90.3 FM on our homebrew receiver from Radio Design 101, augmented with our new Q-enhanced low noise amplifier. I've got the LO tuned to 79.6, which would give us 90.3 if we had 10.7. So let's turn that on and see what we get.
Else just follows after that. You can probably choose the order after that, however you'd like, so, I guess, to a certain extent. But I would say the first and foremost.
And you can find a little bit of material on this in Epilogue 3. But we've gone beyond that, and I want to play you a little clip now of what you can do with it. This is going to be using this same radio, but we're going to put a front-end filter on it. Take a listen.
I love throwing away expired stuff. Like, that gives me joy. But sentimental things, that's another story.
So that was using a more recent prototype of the front-end filter that you can see here. This is a layout in KiCad. And this is me over in the upper right. And this is a grad student working on this project. These are his boards here. And this is another faculty member at the school. So the result, using this new technology, is that our little radio that we designed in Radio Design 101 outperformed all 3 commercial radios. Now I say 3 because I added in a newer ATS-25 radio down here, a digital signal processing radio. It did pretty good, as you can see in this column, but even it wasn't able to receive this really weak station at 88.1, which is at minus 96 dBm. Let's take a look at that over here on the spectrum analyzer plot. That's right here. You can't even see it, which probably explains why it's reddish colored here. Green means received well, reddish means not very usable, and red means nope. So this is a real challenge to receive something that's minus 96 dBm. That is close to, within about 10 or 20 dB of the theoretical noise floor for an FM broadcast receiver. But in the presence of all these strong interferers, you can't receive it with most radios these days. Even the spectrum analyzer. We'll go into in this video series why the spectrum analyzer couldn't really show that signal, but it's there. And with the addition of the new fancy Q-enhanced bandpass filter, this is a KiCad rendering in 3D. We just swapped it out for the low noise amp and the Radio Design 101 guy. We could receive that station pretty well. So that's what we're talking about. How to receive signals in crowded spectrum environments. So here's the outline for the rest of episode 1. We've kind of done an introduction, but we need to talk more technically about what's going on. And so when we come back in part 2, we'll look at something called the blocking problem and the intermod problem that I talked about here today. And we'll go into this block diagram in more depth and look at the signals as they pass through all these different blocks. And we'll look at additional receiver architectures, bringing us all the way to the direct conversion receiver designs that are used in radios like this guy, the 2024 software-defined radio, the ATS-25. which could not get our weak signal, but we can. So in part 2 and beyond, we'll cover these topics and show you where this research started, and we'll look at circuit level solutions, simulations, and real life scenarios. So that's it for part 1. I hope we've begun to satisfy this definition of a white paper, showing you what could be done in future radio designs.